Good afternoon. My name is Artur Pilipenko. Ivan Krylov is my colleague. We both work at the compiler team at Azul Systems. And today we're going to be talking about the compiler which we've been building for the last several years. And we'll start with a brief explanation what Falcon is and why the hell we decided to write a new compiler. Then we'll discuss LLVM a bit and also give some explanation why we chose LLVM as an infrastructure to build our compiler. And the large section of this presentation will be about the hard work we made in LLVM Upstream in order to make a high-performance JIT for managed language. And it was more difficult before. And in the end, I will give mic to Ivan, and he will share how this compiler fits with existing technology we have, like ready now, and what kind of cool technology it enables, which we will not be able to do before. So Azul Systems makes Java virtual machines, and our flagship product is Zing JVM. It is a commercial server VM historically built on Hotspot, but evolved differently, and it has several technical key features which differentiate it from Hotspot. And primarily, Zing is known as a low latency virtual machine. We have a great garbage collector. It's low pos. It scales well to heaps up to 8 terabytes today, but that's out of the scope. We have ready now technology which eliminates latency spike caused by deoptimizations, and it also improves the warm-up of your application. And recently we got a new compiler. So if I were to tell you about Falcon in one slide, I need to tell that this is the final tier compiler in our VM. It is a replacement for C2 compiler, and it is based on LLVM. The development of the new compiler started in 2013, and in December 2016, we had the first release which included this compiler. And only 6 months later, we enabled this compiler on by default, and by now we have customers which run this compiler in production. Up to the switch to on by default, we had a team of 4 to 6 people working on this compiler, and we estimate that resource investment at around 20 man-year. And now we have all the compiler team working on it because it's our main compiler. So why did we decide to spend 20 man-year to write a new compiler? So we used to have the same, we used to have C2 just like Hotspot and OpenJDK. And our C2 shared same strengths and weaknesses as Hotspot C2. It was a good compiler for its time, but now it's past its prime. It's a very complicated piece of technology which over time accumulated technical debt, and now it is very difficult to maintain and even more difficult to evolve. But that's actually what we want to do with our compiler. We want to improve the quality of the code we generate. We want to write new optimizations, and we want to have some competitive advantage in the compiler as well. So we clearly could not do that and could not afford that with C2. So we started looking for different alternatives, and of course, writing a new compiler from scratch is too big of a task, and we decided not to do that. Instead, we started looking into different open source compilers which we could reuse in order to make a new compiler for our VM. We looked at GCC, Open64, we looked at Graal and LLVM. Well, we didn't have a chance to look at IBM J9 because it was not open sourced at the time. And after eliminating some of the options, we basically ended up with the choice between Graal and LLVM. Graal is a JIT for Java, written in Java. At the time when we started looking, it was a functioning compiler, and it was a very appealing choice because with small resource investment, we could get a new compiler in our virtual machine. LLVM, on the other hand, was mainly used as a static compiler, as an infrastructure for static compilation, and using it as a JIT for managed language would take a lot of infrastructure work. But there were a couple of factors which affected our choice. First, we expect that C2 in OpenJDK will also be retired at some point. And the natural replacement is Graal. It's already part of OpenJDK as an AOT. And the moment when OpenJDK gets Graal, well, we would lose this competitive advantage. And the second aspect is Graal is mostly driven by Orca labs, and LLVM is developed by a very large community. And we wanted to leverage the community effort as much as we could. So we decided to go ahead with LLVM. So if you look at the website of the LLVM project, it says that it's a collection of tools for building compilers and tool chains. And you can find it in many different compilers. And the most known user of LLVM is Clang. It's the compiler for C, C++, Objective-C. Apple's Swift compiler is built on LLVM. There's Haskell compiler, Rust, Julia, D, many OpenCL implementations. And as I said, LLVM is driven by a very large community, and it consists of very big players in the market. And currently it's estimated that there are about 500 active developers in the community, and arguably it's more than total number of hotspot developers in OpenJDK. The project started in year 2000, and by now it's in a very stable and mature state, and it delivers really good performance for C and C++ code in Clang compiler. The corner case of the infrastructure is LLVM IR. It is a classic SSA form intermediate representation with explicit control flow, unlike C2 or Graal, and it can be viewed as a general purpose high-level assembler. And the infrastructure provides various analysis for this representation, so you can query different facts about the program in this IR. You can transform the IR to equivalent but better representation. There are backends for all major CPU architectures, so you can generate the native code corresponding to the IR. And there are a lot of tools to help you work on this representation. And tooling is one thing which we missed a lot when we were working on C2 compiler. So a typical compiler built using LLVM looks as follows. You have a front end which takes the program in your language. It generates LLVM IR, then feeds this IR to the optimizer, which consists of LLVM buses. Then it uses one of the existing backends to generate native code. Can be generated to file for static compilation or generated in memory for immediate execution in case of JIT compilation. So if you were to write your own compiler using LLVM, you need to implement the front end, which would take your program, produce LLVM IR, and then the rest of the work can be done by the infrastructure. So that's what we did at the very beginning. We linked our virtual machine with LLVM as a library. Then we implemented bytecode front end, which takes Java bytecode as input and produces corresponding IR. And this front end is very, very simple. It doesn't do any optimizations. It is intentional because we believe that all the complexity should reside in one place, in the optimizer. Then we used some optimizations. We used x86 backend. It is our only supported platform. And then we get back an object file from LLVM. So we taught our VM how to install it and how to start executing it. Soon we started tuning the optimizations. We started introducing new passes to LLVM. We started tuning the pipeline. And that's how we got Orca component. Orca is our fork of LLVM. And it can be viewed as a LLVM-based JIT compiler for Java bytecode. An important detail here is that it is not tied to Zing, and it's not tied to any particular virtual machine, so it can be used with any other VM or it can be used outside of any VM. So we got our customized optimizer, and as I said, Orca is not tied to virtual machine implementation. But when you are compiling code in managed environment, you want to ask some questions about the code being compiled because the VM knows a lot about it. So, and because our compiler is not tied to the VM, it cannot use internal APIs of the VM. So it has to interact with the virtual machine through a well-defined interface. And this can be demonstrated on this simple example. Here we have some static final object field. It contains an integer, and we have a foo method which just checks the type of this object. Well, we know that the result is true, but as I said, our parser is simple. It doesn't do any optimizations. So it would generate a code sequence, something like that. It would generate a load, then it would generate a code to get the type of this object, and then it would generate a subtype check. And this code sequence will be passed to the optimizer, and optimizer can start transforming this code, asking questions to the virtual machine. And at first it will ask, well, what is at this? Do you know what is at this address? And the VM will say, yeah, I know this is a compile time constant. And then the optimizer can ask, what is the class this object implements? So we can constant fold this call. Can eliminate the load. We no longer use the result of it. And now we have another, we have a subtype check with compile time constant arguments. So we can ask the VM, what is the result of this type check? And the VM would look at the class hierarchy and tell that this is true. So you can ask various questions to the VM, subtype checks. You can ask the VM to devirtualize a particular indirect call for the given receiver type. And you can ask the VM to generate IR for a particular method, so the optimizer can later consider this method for inlining. So the final scheme looks something like that. So we have the VM callbacks mechanism, which is the well-defined interface for interacting between compiler and virtual machine. So now let's talk about what it took us to make a Java JIT from LLVM. As I said when we started, LLVM was mostly used as an infrastructure for static compilers. And well, Clang is the main and most known user. At the same time, there were a lot of experiments to use LLVM as a JIT for managed language. But almost all of them, they were purely experimental and died soon after they appeared. And one of the examples is Shark compiler. It was an experimental LLVM-based JIT in OpenJDK. As far as I know, it never reached reasonable performance, was abandoned, and last year the sources were removed from the code base. So clearly something was missing in LLVM, which made it difficult to make a JIT from LLVM. And we identified 3 areas where we needed, which we needed to improve. It is support for precise GC, it's support for speculative optimizations and deoptimizations, and it is support for Java-specific optimizations. We will go through them one by one, and I will tell in details what exactly we had to do. So let's start with support for GC. So the main question in compiler and GC interaction is, when you're executing code, when you're executing compiled code, how does GC find the references on the execution stack? They can reside on the stack, they can be in registers, and the typical answer is, well, mechanism of GC Safepoints. At this point, GC can ask a thread to pause, and then can parse the stack and get the references from the execution stack. So when you have a thread at a save point, the compiled code can be at the very top frame and can be at a save point pole, or it can be one of the frames below, which led to execution of this frame which had a Safepoint poll. And at any frame, the GC should be able to parse the stack. So from compiler standpoint, GC should be able to parse stack at call sites, and we can represent polls as call sites as well. The other side of this interaction is that if your garbage collector can relocate objects, your compiler has to be aware of that and has to expect that. So here we have some object O. Before and after a call which can have a Safepoint, the object and properties of this object are the same, but the bitwise representation of the pointer can be different. So from compiler perspective, it should be something like that, where O before and after are different values. So in order to implement this kind of interaction, we introduced a concept of GC state point to LLVM. It is basically a way to wrap a function call, so this call is reported to GC and relocations are reported back. So it takes arguments for the call, it produces return value, but it also takes a set of live pointers which need to be reported to GC and returns a set of potentially relocated pointers. It is represented in LLVM IR as an intrinsic. It takes the target for the call, it takes the set of arguments for the call, and it takes a set of pointers which need to be reported. And when this intrinsic is lowered, when we compile it, we generate a normal call to the target, and we also generate a stack map which describes the state of the stack at this call. So GC can parse the stack using this description. So by introducing this, we set the interaction, but we broke a lot of optimizations. The thing is, optimizations don't know that the values before and after relocations are different, but they share the same properties because they point to the same object. So we could go and teach all the optimizations in LLVM about these properties of relocations, but there are a lot of optimizations in LLVM. And the second thing, when somebody introduces a new optimization, it's unlikely that they will think about properties of relocations first. So instead, we decided not to use explicit relocations for optimizations. So most of the optimizations can be applied to the code which does not have relocations expressed explicitly, but they are implicitly assumed and inserted after the optimizations. And we also introduced a utility path to LLVM, which does the required transformation. So the path called rewrite state points for GC. It takes the intermediate representation without GC relocations and inserts them explicitly. So our optimization pipeline looks as follows. So we have a vast majority of optimizations happening on implicit representation. Then we insert the relocations, and then we have some amount of low-level transformations. So that is it for GC support. The next thing which differentiates static compiler and a JIT compiler is if a JIT compiler cannot prove some fact about the program, it can assume that, well, it will still be true. And if it's not, it can later transfer the execution from compiled code to less optimized version. And simple example, we have a branch, and while executing this branch, we notice that one of the sides of this branch has never been taken. So when we compile this code, we can decide that so it will never happen. So we won't compile the side of the branch which never happened before. But we didn't prove that, so it can still happen. So we need to do something if it happens. And instead, we would insert so-called the uncommon trap, which transfers the execution from compiled code to less optimized version to the interpreter. So this is a new concept for LLVM, and we needed a way to express this. We introduced an intrinsic called deoptimize, and it is a way to express this control flow in the IR, but LLVM doesn't know anything about the mechanics of this transformation, about this transitioning. So it is lowered to a deoptimize call, and your runtime has to provide the implementation which does the job. Well, let's look at a slightly more complicated example. Here we have a final field, and we have a method which reads this field twice, has a call in between, and checks if two values are the same. Well, we can assume that the value of the field doesn't change, and using this assumption, we can optimize the check at the end and always return true. Unfortunately, in Java, there are a lot of ways to break finality of a field. For example, you can do this using reflection. So let's say we were happily executing foo, compiled version of it, called bar somehow changed the value of the field, and now we need to return back to the compiled code, but it's no longer correct. So, simple answer, we return to the interpreter. This example demonstrates that in compiled code, for any call, we have two potential continuations of the execution. We can normally return to the compiled code and resume execution in compiled code, or we can return to the interpreter. So implicitly, after any call, we have a check if we need to deoptimize, and then we have uncommon trap. We do not generate this in the code. It's what runtime does for us. So I was saying, well, just return back to the interpreter, but it's not that easy. We need to know where exactly we need to return. So for any point where we can transition execution from compiled code to interpreter, we have corresponding interpreter state attached to this point. It describes, so here we have the unfortunate method, needs to be deoptimized. We have bytecode for this method. So we need to know that we need to resume execution from BCI 6, and we need to know the value of local. And in general case, we also need to know the state of stack slots, the state of monitors acquired by the code. And we need a way to express this in the compiler, and we also need a mechanism for runtime to find these values somewhere when we deoptimize. So how do we do that? For that, we introduced a new concept to LLVM IR. This concept is called Operand Bundles. It is a generic mechanism to attach a set of values to a call side. And we use a special kind of operand bundles called Deopt bundles to describe interpreter state for a call. And the second question is, how runtime will find these values and Deopt state associated. It would generate a GC state point intrinsic call, which other than live pointers, has a set of arguments which describe the Deopt state. And if you remember, when we lower a call to GC state point intrinsic, we generate a stack map. And runtime already knows how to parse this stack map. So this is the way how runtime will find the values for deoptimization. So that's it for speculations. And the next thing is Java-specific optimizations. When you compile code in a high-level language, in order to achieve good performance, you need to take high-level semantics into account. And good motivational example for Java is devirtualization. We have a lot of indirect calls. The good news, in runtime, most of them resolve to the same target. So to devirtualize, we need to know about receiver type for the call. And LLVM, of course, knows nothing about Java types. LLVM IR is low-level representation. LLVM doesn't know anything about Java. So in order to solve this problem, we use so-called high-level embedded IR when we express bits of high-level semantics in LLVM IR. LLVM IR provides a mechanism to attach bits of high-level information using attributes and metadata. And we use them to attach information about Java types or values, semantics known by the optimizer. And they can be viewed as a high-level intrinsics. And it's easy type checks and has a virtual call. In pseudocode for high-level embedded IR, it looks something like that. And you can notice that from LLVM standpoint, the type of the argument is pointer to a byte, so it doesn't know anything about high-level information. But we use attributes to add some extra information about the type of the object. So using these properties, we can start optimizing this code. We can ask the VM using mechanism of callbacks, true. Then we have an abstraction call for resolve for a virtual call. And we can also ask the VM, we know the type, we can ask the VM for a single target for this call. And VM will return us, yeah, there is one single target this call will be bind to. So in the end, we have two abstraction calls and we have a direct call instead. As I said before, our optimizer, so the VM has to provide implementations of these functions and optimizations, for example, common sum loads or do something like that. So everything which like most of the things which I talked about, we integrated to LLVM Upstream. Specifically, all the GC infrastructure is there. All the infrastructure for speculative optimizations is there. Large amount of optimizations improvement is there, but not the Java specifics part. For review, we know that other compilers already use our infrastructure, which working with Upstream, we get is that we get extensive testing, Clang pipeline. We get really good and extensive exposure of this code. So we would like to do that, and we often do that. So how do we stand against competition? Here we have latest Zing and one of the latest updates for Oracle. We have a set of benchmarks which include Spec JVM, Da Capo, and several application benchmarks. And their scores, and is in blue, are benchmarks where we perform worse. Everything in green, low pos GC, and Oracle uses the default. So it can be interpreted differently. We have something like 63% win rate. But if the critical code of your application is something like one of these blue benchmarks, probably you won't be as happy. But for these cases, we still have our C2. Numbers on the next slide are trying to break the compiler, and we sometimes succeed. And huge amount of tests ran on OpenJDK with C2. We observe, well, almost an order of magnitude more. We observe about 10 crashes. Now it's time to give mic to Ivan and talk about problems.
Now is the time for true skeptics. I mean, that all sounds too good, or however you look at it, but you got to be skeptical, right? Cannot be detected at the warm-up phase, so they happen arbitrarily late, specifically so that these deoptimizations happen later on, and we have to recompile. Our initial times were not all that bad. And Falcon improves over C2, but these were collected with default flags, but that's not the point of this section. I was going vector optimizations that are done in the LLVM Upstream, get good, lowest better, so iteration time lower, it sounds good, but the compilation time grows significantly. I mean, we knew from the beginning that LLVM is going to be a heavy compiler, but this didn't look very good from the beginning. There are multiple implications. Your warm-up gets slower, your response of a compiler towards a change, deopt storm or a sudden change in what are the times that each compilation spends in a queue. So with benchmark, it has like roughly around 10 methods altogether to be compiled. But if you consider a large application to look with like 1,000 methods to be compiled, you can easily see the scale, how it propagates. What can we do about it? Or some DevOps would say, how do we combat CPU usage that they observe? So depending on which camp you're in, you look at this from different angles, but the root source, the source of the problem is the same. Well, it can really do two things. One thing is basically try to reduce number of compilations. Try use years old, but still worth mentioning. And then we'll transition to something called compile stashing, which is brand new. So right now is a way to put the same application, probably in the same mode, with the same sort of load and so forth. In some ways, it's similar, or the idea was somewhat taken from tools such as reducing warm-up time, because you actually can take away the profiling warm-up period and start using that profile from the beginning. And also it helps to predict what are, in this application, what are the deoptimizations we're likely to see, and therefore predict and not do those optimistic optimizations there. Writing a profile is like a journal. It's a recording of various events that were happening during compilation. So there are several compile threads compiling various methods, and those compile methods were asking different runtime different questions. Some were including like around optimistic optimizations, nullness of objects, uniqueness of implementer, certain. Along with that, here's a snippet of a profile. It's actually a text-based file. It's fairly easy to read. Some would say it's not human readable, but I guess it is human readable. On the right, it's the assembly of a particular method, and as you can see, its profile is basically a serialized full form of a live profile, which answers the questions: how many times the branch was taken at this and that location, how many times we jumped, and so those are the sort of things that every VM captures during execution. We persist that in text-based file. On the replay, read-now profile can provide 2 out of these 3 inputs to a profile. So you still need to get your bytecode, but then you can speculate about what would be the profile if this method was warmed up normally, and also provides the speculative runtime questions and answers. When using it, it's basically feeding. Well, that's actually, although it looks a little somewhat simplified, but one of the hardest part right now is actually matching the classes that were persisted, or information that was persisted about those classes and methods, and matching those with at the replay time. This problem actually gets quite complicated, but goes a little bit beyond the scope of this talk. So on this tiny example that I'm showing, we get away from the unloaded traps, and therefore number of compiles get lower, and with the same score, we get less time being spent in a top-tier compile. So we're going down. That's where we wanted to go, and also our worst operation time goes down because we can predict we don't have to stumble into deopt pitfalls. Now let's go reduce even further, and let's talk about compile stashing. Compile stashing is actually a sort of a step forward from ready now, because in right now we were just persisting like code profile, all the various meta information. Compile stashing is about preserving the actual results of a compilation, the binaries. Compile stashing, in our definition, is basically a way to reuse top-tier compilation produced in a previous run. It is even more beneficial. It is different from Java. It's the one that captured all the profiled information, similar to the ones that JIT has, and I'm going to talk about that in a little bit. LLVM are in a mix of the ones that are provided by the LLVM community, or the pipeline, and the ones that we write on our own, and they're seen as a proxying cache between this JVM and Orca component. Thanks to this very separate, construct the same initial IR and go ask the cache, okay, was this cache ever observed? If so, then what were the associated? And if they do hold true, then the request is go fetch the binary. And then the binary is installed. Of the compilation crashes when they do happen, it is the whole actual design came from the early work that was actually designed to debug. Combining the two, if now there's a VM, it first asks this hash. Well, was this method ever seen? And if so, provide it to me. If no, go ahead and do the full-blown compilation and store it so that our cache becomes richer. And over time, it becomes more and more rich, and we don't need to do live compiling. We'll be doing it less than before. Going back to the same benchmark, we are now down to 53 milliseconds. It's still quite a bit, but there's plenty of room for improvement in compile / lookup. There's some operations that still have to do what could have been light and yet have a much better throughput. So is this problem solved? Well, I was showing an example where things match really nicely. In the real world, by saying real world, we mostly actually have the data from our lab rather than real user, because those only start to emerge. But the match rate is somewhere between 10 and 50%, depending on the workload. Some of the problems are the ones that JIT has. For example, the famous problem of class loaders. Class loaders were designed the way that in the VM they are just an object, and to be able to locate that same class loader and the properties of classes that were in the same class loader on a replay gets fairly hard. Also, a problem with instrumenting agents. So it's one thing that was stored in the class file, and it's another thing that VM sees when transformations were performed. If those transformations are the same, we're actually in a pretty good position because we observe the same state and then we'll stash against that transformed class. But if that instrumentation changes, then we may have a bit of a problem there. But we're not alone. And also generate on the fly classes do pose problems for these ahead of time systems. Where to try? Reading now is available for the last 3 years or so. Falcon, as mentioned earlier, is available on the market since, but it is there. So Falcon that we covered today is our new compiler that is production quality. It's running in product. It's actually turned on by default. So whoever uses Zing by default without flags, they are using Falcon. We're fairly confident with it. Also, the pace of innovation is much faster. We are fairly well improving on existing benchmarks, something we could not do with the old C2. So it's moving a lot faster for us. And while working on things like longer compile times, we start developing some technologies which are still in development, but they will help us to persist compiles and reuse those. And this actually has a lot of implications. I'm pretty sure that in the following years we'll have more reports on how this changed the whole paradigm of runtime and compilation. A lot of work has been upstream to LLVM Upstream, as mentioned earlier. We have a good reputation amongst the LLVM community, and they appreciate the work that's done there. So it's good to be part of that community. So with that, I would like to turn to questions, and thank you very much. Yeah, go ahead, Chris.
Maybe I missed it, maybe you brought it up. So when you match the classes or the methods to the stashed ones, basically, did you introduce some fingerprinting or something like this?
The question was about when we try to match the profile recorded previous run on, and we try to match it to the current run, did we have to modify classes so that they are more matchable? The answer is yes and no. So, if the compile station, although I talked about it as a kind of a continuation of ready now, can also be seen as a separate component. And a more simplified picture is basically compiler getting the same inputs, and if the same inputs were verified, we provide, hey, we don't need to compile it, here's an output. Because compiler by itself is a deterministic machine. What it gets as inputs may contain some speculations but the compiler itself is deterministic. So we verify that the inputs to the compiler are the same, and then we can provide, and then we can install the object. So if you are alluding to things like class loading, identification classes and class loading, there it gets more complicated. There are cases when we can easily identify, things primarily that are loaded with the Bootstrap class loader or the system class loader. But if you come to custom class loader, that's pretty much the work in progress, I would say.
We have to introduce fingerprinting. Like you have to hash the bytecode to know if it's the same. For AOT in OpenJDK, we had to introduce some fingerprinting support. No, yeah, I know. I'm simplifying things, but.
So okay, so going back a little bit to ready now, in order to verify that the profile that we're applying are the same as the ones that were captured, we actually do fingerprint, and we verify that the classes that we're seeing are the same ones. So that part is similar. I think we use like 64-bit hash or things of that nature. So yes, there is no fuzzy matching, although it could be done, but at this point we pretty much rely on the fact that, or we need to ensure that the class representation is from first to last byte identical to the ones I've seen before, which is not the case with generated classes generated on the fly. They often contain whatever, even a timestamp or even some meta information. So similarly, we can match, like, for example, if we're running product and and we have fuzz debug, and fuzz debug would contain more checks. The body of methods in those classes were different. We can't really match. So we have in the labs we have fuzz debug in product, but we only have to use the same. If it was produced by product, it has to be reused by product as well. And things like that. Yeah. Yes, John. That is also a work in progress. So to tell you the truth, the industry is fairly severe behind the language changes that are introduced by language designers. So even transition to all the nice features of Lambdas and Stream API is still happening at more or less, well, I would say the rapid adoption of Stream API only happening the last couple of years, maybe a year, although it seems to you like ages before. So we were primarily focusing on cases which are more viable to people that use Zing today. We do see though a growing adoption, so it is becoming a bigger problem than it was, let's say, a year ago. So we will have to change like lab form representation to make it more batchable, because right now it's fairly randomized indeed. Yep. And this is one of those things which probably JIT suffers as well. So we actually may need to work on this together, or at least we need to propose and discuss this in more open, I guess. Do we have time for any more questions?
Go for it. One more.
One more.
I have more questions.
Okay, two more. You go first. So I mean, what's the main driver of the sort of much higher compilation time in LLVM? And then I mean, what have you tried to address? I mean, to address it, because when you're doing JIT compilation, you're more sensitive to that than LLVM traditional data, right?
Do you want to take that one?
Do you know what the main driver for the compilation time is in LLVM?
Well, first I will address the statement that in JIT,
Is
in
the
JIT
microphone
we,
on? The other one?
Yeah.
that in JIT we are sensitive to time. At the very beginning, we decided that, well, we are targeting on big server workloads, and at first we did not do much about compile time. And in fact, for many of the customers and many of real life use cases, it's fine. But yeah, we do see sometimes cases when we need to do something, and that's that was addressed. And talking about specific things, one thing is that in doing one like complicated analysis, for example, which computes all the facts you need about values. They tend to have multiple small isolated analysis transformations. Then you combine them together and you get the complexity of that. Like you handle most of the, like maybe most of the cases you could handle with complex and monolithic analysis of transformation. It's more manageable from like developing the compiler perspective, but it has some costs in like you pay for better abstraction. We also know that the way we construct our pipeline, we did not do much about compile time, so there are things we can address there, but there are some fundamental things. So we like I don't know.
Can I add a comment that in the long-term thinking we're trying to do, we look at this as it's been 20 years since C2 was built.
Yeah.
We've gotten 10,000, and that means let the compilers free, so what if it takes longer? We could servers, programs run more than once and more than one place, then we could get a two-order.
Unity. You may remember -ser, -client, corresponding to C1, C2. Now we still see low, too unresponsive, and that meaning has changed. So we're probably in a few years.
I'll just cut this short and summarize, and there are really no other plans. We have step up to the stage, please. We have some speaker gifts for you. Nations, food, stuff like that. So, in your name, I guess. I must say that this was a really dinner, which I hope you join me for. Will be at 7 o'clock at the Shutterfisk Bar if you want to go there with me. And please give these great people a